Here is a scenario that reads like a nightmare. Imagine a node that can receive all messages sent to it, but any outgoing messages from that node are dropped or delayed by a network fault. The node is working perfectly. It is receiving requests from other nodes. It processes them. It sends back responses. But nobody hears the responses. After some time out, the other nodes declare it dead. The situation unfolds like a scene from a horror movie. The semi-disconnected node is being dragged to the graveyard, kicking and screaming, "I'm not dead." But since nobody can hear it screaming, the funeral procession continues with stoic determination. Now consider a third scenario. A node experiences a stop-the-world garbage collection pause for 1 full minute. All threads are paused. No requests are processed. No responses are sent. The other nodes wait, retry, grow impatient, and eventually declare it dead. The GC finishes. The node's threads continue as if nothing happened. As far as this node is concerned, almost no time has passed. It starts cheerfully chatting with bystanders, blissfully unaware that it was just declared dead and replaced. The moral: a node cannot trust its own judgment. A distributed system cannot exclusively rely on a single node deciding things for itself. Instead, distributed algorithms rely on a quorum voting among the nodes. Decisions require a minimum number of votes from several nodes to reduce dependence on any single one. The quorum is typically an absolute majority, more than half the nodes. With 3 nodes, 1 failure can be tolerated. With 5 nodes, 2 failures can be tolerated. And crucially, there can never be 2 majorities with conflicting decisions at the same time. The mathematics of majorities prevents split brain. This is what it means when the book says the truth is defined by the majority. Even if you are alive and healthy and know with certainty that you are the leader, if a quorum of nodes has voted to depose you, you are deposed. Your individual knowledge does not matter. The quorum decides. Understanding that nodes can be incorrectly declared dead is one thing. Preventing the damage they cause when they come back to life is another problem entirely. Consider a distributed lock. You need to ensure that only one client can write to a file at a time. To implement this, you require each client to obtain a lease from a lock service before accessing the file. If multiple clients write simultaneously, the file gets corrupted. Here is what goes wrong with a naive implementation. Client 1 acquires the lease. Then Client 1 experiences a stop-the-world GC pause. The lease expires. Client 2 acquires the lease and writes to the file successfully. Client 1's GC finishes. Client 1 wakes up, checks whether its lease is valid, and from its perspective, with its frozen clock, the lease is still valid. It writes to the file. Now both clients have written, and the file is corrupted. The fix is elegant and is called fencing. When the lock service grants a lease, it also returns a fencing token, a number that increases monotonically every time a lock is granted. Think of it like a ticket number at a deli counter. Client 1 gets token 33. Client 2 gets token 34, it's always higher. Every write request must include the client's current fencing token. The storage service remembers the highest token it has seen and rejects any write with a lower token. So when Client 1 wakes up from its GC pause and tries to write with token 33, the storage service has already seen token 34 from Client 2. It rejects Client 1's write. Data corruption is prevented. In Zookeeper, the transaction ID ZXID and the node version serve as fencing tokens. They are guaranteed to be monotonically increasing. The critical insight is that the check must happen at the resource itself, not at the client. A client with a stale belief about its own authority will always think it has permission. Only the resource can enforce the correct ordering. This is a broader principle: do not trust nodes to correctly identify their own authority status. Give them tokens, and let the storage layer do the enforcement. Fencing tokens handle a node that is mistakenly wrong. It believes it holds the lock when it doesn't, but this is an honest mistake caused by a GC pause, not malicious intent. But what about nodes that deliberately lie? A Byzantine fault is when a node sends corrupted data, claims to have received messages it didn't, or acts maliciously to subvert the system's guarantees. The problem of reaching agreement in the presence of such nodes is called the Byzantine generals problem. The name comes from the difficulty of Byzantine military generals trying to coordinate a battle plan when some of the messengers are traitors who may deliver false messages. Most distributed systems in everyday engineering assume non-Byzantine faults. Database nodes don't deliberately send false data. A server might crash, might go slow, might drop messages, but if it responds, it tells the truth as best it knows it. This assumption is valid for data centers where you control all the machines and trust all the software. Byzantine fault tolerance is required in different environments, aerospace and nuclear plant control systems where hardware may be affected by radiation. Bitcoin and other blockchains, which must reach consensus among participants who don't trust each other. Some multi-organization systems where different organizations' nodes might have conflicting interests. Beyond fault types, the book introduces 3 system models that capture timing assumptions. The synchronous model assumes network delays, process pauses, and clock errors are bounded by a known maximum. This rarely holds in practice. The partially synchronous model assumes the system is usually synchronous but occasionally violates the bounds closer to reality for most systems. The asynchronous model makes no timing assumptions at all, the most pessimistic model, requiring algorithms that work regardless of how long things take. The book's conclusion is that distributed systems require us to reason about possibilities, not certainties. We cannot know, we can only reason about what might have happened, design for the worst case, and build algorithms that remain correct even when our assumptions about the world are occasionally violated. That epistemic humility, combined with the concrete techniques of quorums, fencing tokens, and carefully chosen system models, is the foundation of correct distributed systems design.